Please let me know if you can see my screen.
Yes, we can see your screen.
Okay, thank you guys.
And
Sorry for the technical trouble. So I'm Rafael Vicente Rosa. I'm gonna talk about the STRM project. Thanks for the invitation, and my apologies for not being in person there. I had some trouble with my visa, but that's being sorted out. So first of all, this presentation here is like a compilation of resources that have been presented previously in different, let's say, topics in the SD-RUN community calls, in SD-RUN trial here in Deutsche Telekom, and ORAN Plug Fest. So the first thanks goes to the SD-RUN community and the team of developers. What I'm going to talk today is about the SD-RUN project, and I had planned a quick intro, but thanks to the excellent presentation of Navid, I'm happy to go quickly through this presentation here. This first slide. What we see is that in the ORAN architecture, we have the definitions of different interfaces as it was presented. These interfaces relate with the different components from the service and management orchestration in the northbound interface. And from the non-real-time rig to the near real-time rig, such as the A1 interface that specifies the policies, enhancing information, and even machine learned models to be transported from non-real-time rig to the near real-time rig. We have also the definition of the O1 interface from the SMO and to the components for the FCAPS definitions. Here would be configuration of each one of these components, for instance. The O2 interface is related to the cloud resources where the run functions are executed. Here we have the definitions of that for the execution of the run functions would be the CU, the DU, and even the other components. So as it was mentioned, the E2AP is, I think, is the core of let's say, a talk when we explain about the near real-time rig. And that is going to concern most of the topics that I'm going to approach in this talk today. As it was defined previously, the E2AP is like a generic protocol by which it defines certain service types, and those service types conceive the mechanism by which the service models, which are some sort of contracts between the XApps and the E2 nodes, and define the functions about how the XApps can extract metrics and control this E2 nodes. Here in this case, the CU and DU components. And it's important to emphasize that the implementation of the service model functionalities or the run functions in the run nodes, in the E2 nodes, concerns the specific features of and stack enhancements in let's say in the CU/DU components. Given the quick big picture, talk about today is the SD-RUN architecture or the SD-RUN project. And the SD-RUN project concerns on the development of a near real-time rig and XApps. In specific, this near real-time rig, this project SD-RUN concerns not only the near real-time rig, but also the development of XApp SDKs, not only for the development of the XApps that were provided by ONF, but as well by third-party XApps that can be developed by other SDKs. And the scope of the SD-RUN project is in this squared, dotted squared and components. And here, what we have is that the SD-RUN concerns the rig, the SDKs, the XApps, but also a run simulator to provide all the tooling that the XApps can exercise the programmability of the service models. it has also a set of white box 4G components for CU, DU, and RU based on an open source stack, and also the interoperability with different vendor equipments, different CU, DU providers. And regarding to that, also the project provides all of the tooling for quality assurance and interoperability, a set of releases that we are going to talk about that. And important to talk is that the project, one of the main concerns of the project is to drive interoperability between different components on this, let's say, architecture model. So here I'm gonna stay a little bit to talk about each one of these components. So the micro-ONOS rig, it's a near real-time rig definition, part of the SDRAM project. And it's based on the micro-ONOS architecture, where this micro-ONOS architecture is a microservice-based controller, network controller, that was enhanced with different components to allow the programmability of the rig itself, a near real-time rig. So to do that, I think the most important component that we have to allow this programmability is the existence of the ONOS E2T component. It's as it says, each one of these boxes are like microservices that can be deployed, for instance, in a Kubernetes cluster. And the ONOS E2T is the component that actually makes the let's say the conversation possible between the XApps through the E2 nodes. In the case of the SDRAM project, this component on the southbound, it talks the ASN1 and also SCTP. Oh, sorry, the ASN1 over SCTP. And on the northbound here, together with the different components, it talks gRPC. So what it does actually is the conversion between internal gRPC structures in protobuf definitions to ASN1 over SCTP. And this conversion is only possible because there's a definition of the ONOS E2 service models. And in this component, it's a repository actually that provides all the mechanisms for this translation to happen. It was created a set of tooling that automates the conversion from the ASN1 definitions to the protobuf structures. And through that conversion, what this actually allows to convert not only the definitions of the E2AP protocol that we have running here, but as well as the definitions of the E2, each one of the E2 service models. And that allows that each one of these service models can be translated from protobuf to basically almost any specific language, let's say, because protobufs allow that to be defined. In that way, each one of these APIs that are exposed by ONOS E2T can be consumed by SDKs in different programming languages. In this case, what was defined is that SDK defined in Golang and another one defined in Python. What these SDKs allow is the definition of all the tooling that the XApps can interact more easily with not only with ONOS E2T, but as well as with the other components in the SDRAM project. And for instance, one of them is the ONOS Topo. ONOS Topo is the component that abstracts the information of each one of the components of the E2 nodes that can be controlled by ONOS E2T. So think, for instance, that here you can have the information about the CU, DU components, their supported service models, and how they can be configured and discovered as well, and discovered as well by the different XApps and different components. And together with this RNID, what we have is the definition of UENIB. That actually, it's a different kind of storage that is defined for tracking the run user elements. So here the information about the handsets that are related to the components on Onostopo. And that was decoupled because the UENIB have certain properties that allow the write and read of components faster than the Onostopo, for instance. On the other hand, what we have is the definition of Onos config component that is a component that can allow the configuration of the other components internally in the micro Onos rig. Take here, for example, the configurations that you could have for the initialization of each one of these components, and included the XApps. So that concerns part of the O1T or the O1 interface. Related to the O1 interface in the architecture, we have a component called Onos Exporter. And this component, it can enable the scraping, the formatting, and the enabling of the exporting of the information from the XApps metrics, as well as the internal metrics from the Onostopo or Onos UNIB, for instance, to a time series database, such as Prometheus and then Grafana. For instance, Prometheus being the database and Grafana being the visualization tool for the database. The component that allows the storage and all of these data structures to exist in this cloud native microservice-based architecture is called Atomics. This allows that certain abstractions that provide, for instance, the existence of distributed applications. So think here the implementation of Raft consensus algorithm, that it's like a backend database that provides the replication protocols by which it can be distributed in the cloud. And the component that we can use to manage and interact with other components and the XApps was defined as a Onos CLI. So think here that this component CLI can consume certain northbound interfaces internally defined by each one of these components here. And even the XApps can have this definition of this interface with the Onos CLI to export metrics and also to allow configuration by this component. Another important component of this architecture is the definition of the extended APIs provided by Kubernetes that allow that certain abstractions in the resource definitions of the Kubernetes API can be used to enhance the operations of the components internally here. A quick example is that it's possible to define certain annotations in Kubernetes manifests that can allow the Onos topo to store these components and be discovered by Onos config in a way that they allow the Onos config to understand what components are configured, like the models are configured in these components and their address respectively. This is all done by this set of components in Onos operator, let's say, package. And one of the latest achievements of the architecture is the composition of this Onos A1T component. And this is related with the specification of the A1 interface. It's a REST interface that allows now it implements the policy-based definitions for the non-real-time rig to be added to the near real-time rig. And what this component does is that it basically translates this REST interface to internal gRPC structures that can be forwarded to the XApps and consumed as policy services, enhanced information service, and maybe in the future machine learning models. I think it's important to talk a little bit more about the SDKs in the case of the abstractions that they allow. So the SDKs, in case of the SD-RUN project, they do not only allow the abstraction layer for the rig, but also they form a way of consuming the different APIs of each one of the components that concerns the SD-RUN project, such as ONOS topo or ONOS UINIB, the RNIB and the UINIB information base. And this can be specific to the SDK implementation of each one of the language that are offered these SDK implementations and each one of the libraries that they consume. But these components allow a test of framework of tests for the development of the apps that can be already directly consumed by the XApps. Such another important feature is also the logging framework that allows the message to be properly parsed and logged in a good format that it can be consumed, for instance, by ONOS exporter. It allows the reference of code samples and guides in each way that facilitates the developer to consume the APIs of the APIs and the SDKs to write the XApps. And there are also tools for ease deployment and development, such as there is in one of the components in the SD-RUN project, the ONOS E2T, it can be distributed into multiple instances. And a part of this SDK, there is existence of a component called ONOS proxy that runs as a sidecar container in the XApp that provides the abstraction of the connectivity of this ONOS E2T components as a single agent. So it creates an abstraction layer for that. So here, I'm gonna just describe a little bit about what was done in each one of the previous SD-RUN releases that already took place. Initially, the definition of the SD-RUN project release 1.0, it was defined the development of the Go-based SDK, the integration of run components and KPM XApp with the E2T component in the ORAN architecture, through the definition of this set of components that I'm going to talk more about later, SD-RUN in a box, that allows the deployment of end-to-end environment for development and testing in a single laptop. In the release 1.1 was achieved the definition of Python SDK in collaboration with Facebook. Together with them, we had the successful definition of a new service model called RC-Pre that allowed us the definition of a PCI conflict resolution use case and the introduction of the run simulator for verification of the plumbing and the service models to the XApps. In the release 1.2, we had integration with a commercial run components, UDU, provided by Radisys. We had, similarly to the PCI, we had using this RC-Pre and some enhancements on it. We had the definition of a mobility load balancing use case. Think here an XApp that was triggering mobility load balancing in the network. In addition to the definition of the RNIB and UINIB components for the RIG platform. And this platform and release 1.2 was part of the SD-RUN trial hosted by Deutsche Telekom in Berlin. That I'm going to explain later. In the SD-RUN release 1.3, there were run slicing service model that was defined for a 4G implementation in this white box OpenStack that we had. Also the definition of another service model for mobile handover. So two new use case, the implementation of the clustering mechanisms for the E2T component for high availability and scalability. and the upgrade of this ORAN specification of the E2AP protocol to the version 2.0. And the latest release that we have is SDRun 1.4. This release concerns some implementations of a new XApp for traffic steering that was developed together with Remedo Labs. Support for a Python SDK for an application regarding connectivity management by Intel, where they were triggering mobile handovers using machine learning models. Here we had the evolution of MHO source model to the version 2.0, the enhancement of the run slicing use case, not only using downlink, but also as well as using uplink, and a previous integration of 5G small cells that was done with a partner's Circon. All of these are the topics that are highlighted here. I described in the community calls that were previously recorded and available in the YouTube channel. So I'm gonna send you the presentation slides, and it contains the links to that. To give a summary of what was implemented and the integration aspects, what we had is for each one of the use case that we have here on the left side, we have the definition of the XApps that enable this use case using the service models and by whom those service models were defined, with which components they were integrated, and the protocols, E2AP version of the protocol that it was integrated. So this is part of the release notes of the SDRun project, and you can observe the evolution of the XApps, the service models, and also the E2AP integration tests with a run simulator and also with white box, for instance, implementations. So to give a good example of the two use cases that were defined, one of them is mobility load balancing and another one is mobile handover. Both of them were defined based on two service models that were specified by ONF and other partners. In the case of mobility load balancing, the control that the components had over the E2 nodes was actually defined by the configuration of a control parameter, cell individual offset, that programs let's say, the CU component to trigger the handover of a UE during a A3 event. A3 event is basically a A3 measurement report that the UE sends to let's say to the network, to the G node B, when it sees that the neighbor cell or the secondary cell has a RSRP signal better than the primary cell by certain offset. So by triggering the control about this individual cell offset, it's possible to trigger the load balancing of the UEs among the cells. And that was done by one XApp developed by ONF and another XApp that was developed together with Facebook that were integrated with AirHop EZone server. That was actually a third-party XApp integrated in the RIG platform. That was integrated with RunSim and also with CUD components of Radices in the SDRun trial in Deutsche Telekom. On the other hand, another aspect of use case developing related to handover is that the mobile handover is actually a more kind of active example of triggering handovers, where the service model that was developed by ONF together in a use case with Intel, it allows the programmability of the network in a way that the RIG himself triggers the handover of the UE between the cells, and it does that not only using RSRP and information about the cells and the neighbor cells, but also other components that were part of this service model, such as the RRC status of the UE. And this was integrated with a run simulator, not supported in CUDU components, and was part of this SDRAM release 1.3. It's important to know here that the ST-run components allow the definition of the own service models by a developer. And there's even a tutorial that explains how to do that and how to integrate that in the platform. And talking about the integration, I'm gonna go quickly about talking about the run simulator. The run simulator is the component that allows the definition of the functionalities between the XApps and let's say two nodes. And it was coded to validate the service models that were developed and enabled by the SDRAM project in a way that the same service models that can be enabled and functional in the run simulator, if supported by other components, they can be integrated in different components, such as the KPM service model that was enabled in the ONF run simulator, this white box 4G CUD components, and also it was enabled in a vendor component, in this case, the 5G Redis CUD components. So the run simulator is basically a set of libraries that allow the definition of a topology, and this topology contains a set of cells or E2 nodes and their respective cells. Here we don't have the abstraction of what is a CU or DU, but we have abstraction of what is a G node B, for instance. Each one of these E2 nodes contain E2 agents that make the reference with ONOS E2T component using SN1 and over SCTP. The topology allows the definitions of the UEs, and these UEs, they contain certain properties that can be controlled, that induce them to attach, move, and manage their routes, for instance, and the parameters that they have, such as their RRC state, the RSRP, and the primary and the target or neighbor cells. And all of this is enabled by this what we call mobility handler and radio emulation of the libraries of the run simulator that trigger the mobility of the UEs and the update of the events. And based on the update of these events by this, let's say, radio emulation and mobility handler, together with the radio resource management library, it triggers the events that conceive the interface of the service models through the E2 agent to the ONOS E2T component, for instance, or to E2T, any kind of E2T controller. From the run simulator, it also allows the definition of, as I mentioned, the extraction of metrics or properties from the topology or the model that is being simulated. And here you could have the example, the extraction of the cells. This was done, as I mentioned, enabled by the ONOS CLI component. And it also allowed the definition of parameters for each one of these components, such as the cell A3 event offset value. Here is just an example about how the A3 handover is defined by the run simulator. The A3 handover events are defined by, for instance, the radio resource management library, from where the A3 event is triggered, and based on this trigger of the event here, the library that conducts the handover, it analyzes if the handover was triggered by this event, and if that handover was triggered based on the UE mobility and the change of the location, then it updates the RSRP of the serving and neighbor cells for that UE, and that triggers the events of the service models. For instance, in the case of mobile handover, it would trigger an event of RSRP or RCUE connected status, and the mobile handover service model or application would trigger a specific handover for that. And another point is the white box support of the SD-RAN project. The white box support was defined based on the open air interface component on the 4G stack, where these components were executed in Intel NUCs and together or separated. And what was defined was the establishment of E2 agent, not only in the CU component, but later also in the DU component for the run slicing service model use case. And this E2 agent elaborates the abstraction of how the KPM service model, for instance, can be implemented on top of this stack. These tests that were performed with these components were defined not only using actual LTE handsets for GUE handsets, but also using OIE LTE emulation of the UE components, communicating via USRPs. And the integration tests that were defined in nightly tests, for instance, running to validate the service models and the use case, we're executing end-to-end definition of a connectivity test from the 4G core and the uplink internet link until the UE. So think here that one test that was executed was the definition of this topology in an execution environment, where we had an actual UE, and this UE was triggering the attachment to the network, and the test was validating if the KPM XApp was reporting actually the attachment of the UE in that particular cell. This definition of the white box scenario, together with the execution of the run simulator and the other XApps and the whole near real-time rig, can be easily defined using what is called SD-RAN in a box, RIAB. RIAB is a set of scripts that facilitate the creation and the execution of tests regarding this the near real-time rig with run simulator and white box components in a single computer, it can be even a single laptop. And the idea is that the user can create a simple environment for quick automation of execution of tests and also development process. So for instance, it could develop a new service model or validate a new service model using the writing of a new XApp, deploy this XApp quickly through the Helm charts of the Micronos rig and deploy them to validate with a run simulator or CUD components of open air interface in the 4G stack here. Finally, I just would like to talk about where these integrations were also performed with an actual 5G deployment. And this was the SD-RAN trial that was hosted in Berlin by the Deutsche Telekom Digital Innovation Arena. And in this trial, we had the validation of KPI serves, let's say KPM service model for the extraction of key performance metrics for mobile telemetry of the network. We had also the execution of the PCI use case, where we had the resolution of physical cell conflicts. And we also had this, as it was explained, the execution of the mobility load balancing XApp to control the handovers between cells, between UEs in cells. This setup was actually an real setup, end-to-end, where not only the SD-RAN components were defined in a cloud edge environment, but as well in a um, central cloud or a hyperscaler cloud. The version of the SD-RUN that we had here was a release 1.2, as it was previously mentioned. We had this integrated with actual 5G radios. In the 4G side, we had the OAI stack, just as a reference setup. In the 5G side, we had the radio components provided by Foxconn. The CUDU components we integrated with Radisys components. And the core, as well as 4G and 5G, was integrated with the SD Core project and SD Fabric project by ONF. Everything was operationalized by this Ether management platform that enabled, for instance, the programmability of the components to be deployed both in the edge cloud as well as in the central cloud. Here, for instance, is just an example, but the 4G and 5G control planes, for instance, could be deployed in the edge cloud. So this this setup was actually implemented during the first 2 years of the pandemic, and it was very difficult to make the integration tests. We had these photos of the initial setup of the lab, where we had the testing case of the radio units, the CUDU components, and here the Ether Edge Cloud. Here's the photo of the courtyard in the Deutsche Telekom arena, together with the poles where the radio units were installed. This was only possible to be achieved because actually we worked with different integration labs. One of them was ONF in Menlo Park, where we had CUD components in a virtualized manner together with UE simulator provided by Radisys, where we had integration with the 5G SD core and the XApps. In Radisys, we had another integration lab where Radisys ran CUD components with their own SD core, with their own 5G core, sorry, testing the ONF RIC and the test XApps. And the closest one that we had is the lab that was integrated in the Facebook, where they had almost the full setup with the SD core and so on, but they had the Foxconn indoor radio units. And in Deutsche Telekom, what was done actually is the definition of the same setup, but with Foxconn outdoor radio units. In each one of these stages, they happen kind of like in parallel. We had many issues with SD core integration, with the XApps definition, the service model validation, the test case that we defined for each one of the XApps, and as well as the definition in the case of the end-to-end setup of types of UE handsets they were actually providing expected and consistent behavior to attach to the network and present end-to-end connectivity. These results of this trial were also presented last year in ORAN PlugFest. By the end of the year, ORAN and TIP PlugFest, where we presented the results of the end-to-end, for instance, performance measurements, the validation of the use cases in the actual setup, and in different setups as well. The validated KPM and PCI XApps, the mobility load balancing that we had handover between two cells. And that was specified with the definition of the RC pre-service model and the other ORAN specifications. That was back there, it was E2AP 1.1, 1.0.1, the KPM 2.0, and this RC pre that was our own pre-standardization service model before the run control service model 2.0. And to end the talk, I think it's important to say that there are recordings of some community calls that happen, of all the community calls that happen almost twice a month. Those are available in SD-RUN YouTube channel. The presentations are available in a Google Drive link for everyone to access it. If people have a need to access the resource presented here today, you can access the mailing list of the STRun Dev or the wiki or the code in the GitHub, the docs in this web page. And if there are any questions, we have active participation of the developers of the STRun project in the STRun Dev Slack channel. So thanks again for inviting. Thanks for allowing me to present here, even in a different schedule. And I'm happy to answer the questions.
Thank you very much, Rafael. Any questions from the audience? Yes, Kostas.
Thank you for the presentation. I want to ask about atomics. It's one of the modules of the elements that was even before in the times of ONOS. And that time it was responsible for keeping the assignment between switches and controllers and for all shared data. Now we have two new modules that have the data for UEs and the other E2 nodes, the ONOS U and B, the two elements above atomics. So what remains? What is the responsibilities of atomics in monos, micro-ONOS?
Well, in micro-ONOS, atomics is still a distributed database that allows the consensus of information between distributed nodes. It basically provides the same functionality, but here it provides just the storage for different data structures that are defined by the ONOS topo and the ONOS UNIB. So
whatever is kept by these two from ONOS topo, let's say, is also shared through atomics?
yes.
Okay. Okay, thank you.
Thank you very much, Kostas. Thank you, Rafael. Any other questions? Any question from the remote audience? Okay, great. Thank you very much, Rafael.
Thank you.